it Wiescher or how is it?
It's Wiescher. It's a German.
Wiescher. Okay. Sorry. Okay.
German, they have it the other way around.
Okay. Professor Wiescher. Okay.
But I'm used to Wiescher too.
So we are live now, sir.
Okay. So maybe before I request Professor Wiescher to speak, I'll give a short introduction. So welcome all to this edition of the Asset Colloquium. It is usually held at 4 o'clock, but today, because we have a speaker from Notre Dame, and because of this time difference, so we have he has kindly agreed to at least come early enough, and so we can postpone it. We have shifted it by an hour or so. We thank Professor Wiescher for that. So let me give a few words of introduction to Professor Wiescher. He is the Freeman Professor at the University of Notre Dame. He works primarily in the area of nuclear astrophysics, but also other interests like doing analysis of heritage objects. I guess through PIXI and things like that at the Nuclear Science Laboratory at Notre Dame. He has been the director of the Nuclear Science Laboratory for many years, 2005 to 2020. He was also the founding director of the GINA, which is the Joint Institute for Nuclear Astrophysics, again for about 12 years, 2003 to 2015, and is still associated with its running. He is presently the director of the Notre Dame Institute for Structure and Nuclear Astrophysics. He has also many other adjunct appointments in Michigan State University, Surrey, and visiting professor at Frankfurt, Germany. He has a large number of publications and also has been honored by for instance, he's a fellow of the American Physical Society. Then he has won the Hans Bethe Prize in DNP and DAP, the Department of Nuclear Physics and Astrophysics, in 2003. He had a Humboldt, I think, Forschung, I guess that's a fellowship or something, in Germany in 2007. He was also elected in 2010 as the fellow of the American Association for Advancement of Science, and received the Harris Visiting Professor at award in the University of Frankfurt in 2017. In 2017, he also became the elected scientific member of the European Academy. It's called the Academy Europea. And in 2018, received the Laboratory Astrophysics Prize in 2000, LADY division of the American Astronomical Society. So with these few words, let me request Professor Michael Wiescher to give his talk on, by the way, he had given 3 options, and then I communicated with some of my colleagues and they chose this option. And this is something, of course, that I have also been interested in a very peripheral way. But so anyway, finally, this is the topic. But perhaps we will have a talk by Professor Wiescher, if he agrees, some other date on some of the other topics. So, Professor Wiescher.
Okay, yeah, thank you. Thank you for the invitation. As I wrote earlier, I would have loved to come in person, but these days it's a bit of a challenge. So, and I have to give the talk on Zoom. So I want to talk about the impact of nuclear structure, quantum structure, nuclear cluster configurations on nuclear synthesis. I think it's a much underestimated role the quantum physics of the nucleus has on the chemical evolution of the element. And I want to highlight that in this talk. So as you can see, I have 6 topics, starting with a very quick overview of the Big Bang and the early star evolution. And that brings us to the critical question of the conversion of the Big Bang nuclei, the so-called primordial nuclei, to CNO elements. The Big Bang itself cannot do, only in very minute amounts, CNO elements. Then I talk about the light isotope clusters, how that may facilitate this transition. And then I will, being from Notre Dame, I have to tell you something about the experimental resources and the experiments we do here in that direction, not only at Notre Dame, but also at the Casper Underground Laboratory in the Black Mountains in South Dakota, where we have a small, rather old accelerator to do these studies. And then I will switch back to the theoretical interpretation. First, I talk about the carbon-oxygen production in the early universe, which one can see in the spectrum of very early stars already. And then some new theme. I will talk about the so-called I process, intermediate process in early stars, which people seem to be very excited about. Anyway, galactic chemical evolution, this is here the overview picture at the top. It's obviously a logarithmic scale. You have the first 3 minutes of the Big Bang, and in the third minute, you have third to 10th minute, you have the Big Bang nucleosynthesis, which leads to the production from literally protons and neutrons to helium and lithium isotopes. And then you have the dark ages. Every light is absorbed until the photons decouple. And then with the first light, you see also the first massive star emerging, which have been formed in the first 400 million years after the Big Bang. And down on the lower scale, you see first the primordial elements produced in the Big Bang. And then in the next thing, you see the elemental distribution in the oldest star, done measured by spectroscopy of the oldest star. That's a little bit older. We have now many of these stars which show comparable elemental distributions. And you see still the same amount of hydrogen and helium, but you see lighter nuclei are now converted primarily into carbon and oxygen. And you see elements going up to strontium, I believe is that iron strontium. So you have to have, in the very first phase of stellar nucleosynthesis, you have to go from hydrogen helium to carbon oxygen and further on to iron. And then on the right-hand side, you see literally the elemental distribution or isotopic distribution as we know it now in our solid system and presumably in the rest of the universe. So at the beginning, I want to start with the Big Bang and the early star evolution. And here's what people think about the Big Bang nucleosynthesis. On the right-hand side, you start with hydrogen and neutrons a little bit after the decoupling of the weak interaction. And neutrons obviously decay into hydrogen, but that takes a few minutes, and we have only a few minutes available for the nucleosynthesis because we are in a rapidly expanding environment and the nuclei decouple. And that means neutrons are essentially converted by this reaction chain to helium-3 and helium-4. And then you have some nucleosynthesis going on, but that is handicapped by the mass 5 and the mass 8 gap, the fact that we don't have any stable nucleus with mass 5 or mass 8. So that prevents the sort of the initially envisioned idea by George Gamow, for example, that the Big Bang produces everything up to uranium. That is not possible just due to the fact that there's no stable mass 5 and mass 8 nucleus. So you stay, as the simulation shows on the right-hand side, you stay pretty much with hydrogen and helium, and orders of magnitudes at the logarithmic scale, lower abundances of deuterium, helium-3, tritium-3, which eventually decays to helium-3, beryllium-7, and lithium-7. Okay, and that is pretty much confirmed by the observations of primordial material in the interstellar medium, except lithium-7 is only 1/3 of the predicted lithium-7 is observed, and up to 1,000 times more of the predicted lithium-6 is observed. So that means there is some lack of understanding, and there's been lots of experiment done to solve this so-called lithium problem. And I don't want to talk about that, but might talk to a certain extent because it involves lithium. may eventually provide a solution. I don't know yet. So the emergence of first stars, that comes in the dark period of the early universe. And you find here on the left-hand side some simulations how that happens. I mean, they are very massive. Predictions range from 100 to 1,000 solar masses. That means they are very short-lived. They live only a few million years and die then in kind of big supernova explosions, either core collapse supernova or pair production supernova, and spread their material through the early universe. The debate on the masses is open. Here I quote 100 to 1,000 masses. Other people quote 5 to 160 masses. So it's really an open debate. That are the conditions from the nuclear physics point of view, and I want to present my talk from the nuclear physicist point of view. So these first stars are made from primordial material, hydrogen, helium, a little bit of lithium. They're very massive. They contract due to their internal gravitational force. In a normal star, in a modern star, so to speak, like the sun, the contraction is sort of stopped, put on hold by the internal energy generation through nucleosynthesis of hydrogen burning. In the sun, it's a PP chain. In massive stars are the CNO cycles, which produce sufficient enough energy to generate the internal pressure to hold the contraction. And on the left-hand side, here is a PP chain. The energy production is limited by the weak interaction-based P plus P fusion reaction. And for more massive stars, the CNO cycle have to take over the energy production and to balance the gravitational contraction. But in first stars, you don't have CNO elements. That means you cannot stop the contraction. So the star, you have a different environment than modern stars, deep convective, as you see it here in a simulation by Klaus Falk-Herwig. So you have an outward flow from, which is sort of indicated by the orange color material, and an inward flow by the blue colored material. So you have deep convection and not a homogeneous environment like you have in modern stars. So it's a completely different environment, different fuels, and different dynamics. So that are the conditions we have to consider, and people are starting to model that. Only modern computation power allows us to do that. So how do we get from primordial to CNO elements? And that it's arc CNO elements in first star you see on this star, so-called Keller star or SMSS 0313670A. That is this guy. And you see basically the abundance distribution relative to the solar abundances, actually. You see here a lot of CNO elements, primordial lithium, that's only the elemental abundances. And then you go up to the calcium range, calcium scandium range. So the question is, how do you get from here to here? Okay, so how are CNO elements formed? And then the second question I will raise at the end of the talk, how do you get beyond CNO up to the higher mass ranges? See here, you only have upper limits. And there are different ways. A classical way, as people thought, is a triple alpha process. So the idea was the star contracts in a homogeneous manner, and you make a little bit PP reactions, but you cannot make CNO because you have CNO. Eventually, you reach densities to allow the triple alpha process, so the fusion of 3 alpha particles to carbon-12. That is the reaction which dominates in modern stars, the helium burning phase. But I want to point out, due to the cluster structure, you can of nuclei, you can also have, and the dynamics of the environment, you can also have other reaction sequences like alpha D, forming lithium-6, alpha-gamma forming boron-10, and then with an alpha-D reaction forming carbon-12, and you resupply the deuterium fuel by emitting a deuterium. So that would be this one, this reaction chain. The red line symbolizes the triple alpha process. And then you have something which is actually, I thought about, 30 years ago, 89, in a paper, what's called the hot CNO cycle. Oh, sorry, the hot PP change allows the participation of nuclei like carbon-11 and nitrogen-12 to bring fast, to facilitate a fast production of CNO materials. I don't want to talk about that, just want to mention. So what are the light isotope clusters which facilitate these processes? And here's the triple alpha process. It's probably well known. I just want to repeat it. It's a two-step process. And you have basically the fusion of two helium nuclei, large abundance of helium in primordial material, to beryllium-8. Beryllium-8 is unbound by 92 keV, immediately decays, but it's a pronounced alpha cluster structure, as you see in the simulation of Canada NU. It decays immediately back to two alpha particles, but you establish an equilibrium between production and decay. And on the small equilibrium abundance of beryllium-8, you capture another alpha, a third alpha particle into this state, the second 0+ state in carbon-12, the so-called Holt state, which has also a pronounced alpha cluster structure. That's what facilitates the capture. So it's basically the important ingredient for making this second step, converting beryllium-8 in carbon-12. Then this state decays by pair production to the ground state, 0+. That is actually the biggest uncertainty, the pair production branch in the determination of the reaction rate of this triple alpha process. But that's a key element. It's a cluster structure. But you can imagine other clusters, and that is actually also observed in photodissociation. So here you see basically the photodissociation, I believe that was from cosmic rays, of nuclei like lithium-6 and boron-10. And this dissociates in an alpha particle and a deuterium. This dissociates in beryllium-8 or two alphas and a deuterium. So you see this kind of process already in nature, and you can envision the inverse process in first stars, D form plus alpha forming lithium-6, and lithium-6 plus alpha forming boron-10, and then boron-10 plus alpha forming nitrogen-14, and you have an emission of deuterium, and then you are at carbon-12 in the CNO range. So we wanted to explore this possibility. And the second interesting aspect is by forming these light beryllium nuclei, beryllium-9, boron-10, beryllium-11, actually that should be boron-11 here, boron-11, you generate neutron sources. There are the elements you don't see in present stars. And, but you can form them in principle in early stars. And they can be a source of neutrons, neutron production in early stars. So here all the possible production reactions for these nuclei, lithium-6, boron-10, lithium-7, boron-11. I only will talk about the center link. And then you can have subsequent alpha N reactions. So in this dynamic environment, and the right combination through the right reactions, you can generate neutron sources. That means you have neutrons available They are died away from the Big Bang. So we have real new neutrons produced in the very first star, and that can facilitate the nucleosynthesis towards the heavier nuclei. So that is all presently being investigated. And here I show you the strengths, the reaction cross-section for the neutron sources. And you see the strongest one is beryllium-9 alpha N. Everybody knows that who does helium-induced low energy nuclear reactions. That is one of the strongest background sources. But then boron-10 alpha N and boron-11 alpha N. And here the standard neutron sources which are being discussed is a carbon-13 alpha N. That's the neutron source for the S process. And blue is the neon-22 alpha N. That's a neutron source for the big S process. And for the N process in supernova also. So I will talk not all, only about two of them, boron-10 alpha N and carbon-13 alpha N. Okay, so I will discuss where do the seed isotopes for these processes come from. And I will, as I said, I will discuss only one branch, that's the lithium-6 alpha gamma, boron-10 alpha N or alpha D or alpha P, forming eventually CNO isotopes. So you see here, that's a R matrix prediction for the lithium-7 alpha gamma reaction to the ground state, to the first excited state, to the second excited state. And in particular, in this branch, you see a broad resonance, which is cluster state in the boron-10 compound system. And that in our latest data, which I will not show because it's still under analysis, it increases substantially the reaction rate for this branch forming boron-10. And here also the same thing, cluster state in boron-10 alpha N, so that is in nitrogen-40 compound nucleus, and you see that appearing in the alpha N, in the alpha P, and in the alpha D channel, facilitating the CNO nuclei. So the important thing is the contributions of these levels, these broad, strong levels to the reaction rates. So what are the experiments we have performed to do these studies? And we did this at Notre Dame, at the local facilities here, and at the Casper underground facility. Just a short overview of the Notre Dame facility. It's a small university-based laboratory. We focus primarily on nuclear astrophysics, me and my colleagues. So our main machine is rather old, is the NEFN tandem, which has a bunch of ion sources, SNCC sources, and two plasmatron sources. It operates an AMS program, and it also serves as a driver for small-scale radioactive beam facilities, actually quite powerful, puts out a lot of papers, has a broad international collaboration here. The second machine is this Pelletron. It's a vertical machine with an ECR source at the terminal. We do most of our nuclear astrophysics experiment here. So in forward kinematics, light ions on heavy targets, or also in inverse kinematics, heavy ion beams on a gas jet target. Right now it's a helium target to do alpha-induced reactions in inverse kinematic, having here the St. George recoil separator. Here's a picture to separate the reaction products from the primary beam with a rejection ratio of something like 10 to the 15. And then down here is the third accelerator, which is primarily used for applications like cultural heritage studies, as mentioned before, environmental material studies, chemical material studies, all sorts of applications. So that brings some additional funding into the laboratory. So that's what we operate primarily, as I said, for the nuclear astrophysics probe. And that is complemented by the Casper facility, which is in the Black Mountains. It's an old gold mine. Was 100 years old, and the company gave it to the state of South Dakota at the time when the gold price was low, and they thought they could not afford it. And now the gold price is high and they regret it, but never mind, it's too late. So we got an area there, and it looked pretty wet and unpleasant at the beginning when we checked it out to build a lab there. But at least it had railway access to bring material there, and we located a small accelerator from our lab to the underground location, which is about 1 mile underground. So this is the present SURF facility. That's the underground facility. It has 2 shafts. We usually use the Yates shaft, and then we have to, that's about 1 mile. And this is here the Casper facility in a remote position. Lots of experiments were here, and because we produce neutrons, so they don't want to have us near. But now they put the LBNA or the Dune facility, the detectors for a big neutrino oscillation experiment, right in our neighborhood. So we're probably going to move somewhere here where the material is less, background material is less radioactive, less uranium and thorium content. That is a Casper facility as it looks now, the small accelerator. It's an old accelerator. We completely rebuilt it, but it put out high intensity beams, mainly alpha and proton beams. So we completed N14P gamma for the CNO cycle, boron 11 alpha N, boron 10 alpha N, carbon 13 alpha N, neon 22 alpha gamma, neon 20 alpha N. There are 2 competing reactions. And right now we're looking at magnesium 25, 26 alpha N. So it has been a very active program, but right now we just last week went to a dormant period. So right now we focus on analyzing the data. The advantage of underground physics, accelerator physics, is literally the background reduction, primarily cosmic ray reduction. You see that here on the top left. When you take a germanium detector and measures above ground, you see basically at higher energies, above 2.6 MeV, the radium-thorium line, you see basically the spectrum is formed with cosmic ray-induced gammas. And when you have nuclear astrophysics reactions, that is where you want to look for your signal. Going under the ground, you reduce it to that black spectrum. Okay. The amplitude of the black spectrum depends on your environment. As I mentioned earlier, the cleanest environment is a salt mine because you don't have radium thorium in there. Our environment is not as good, for example, not as good as Gran Sasso. These pictures are from the Gran Sasso. We have a little bit more radium thorium in our lab, so that's why we actually are not unhappy about moving. Here you see what you have to do with the local environment is basically you have to have local shielding to reduce it by 3 orders of magnitude or so. Neutrons, we focused initially on neutron studies. That is a neutron spectrum above ground. That's cosmic ray-induced neutrons in a helium-3 counter. That's a spectrum, and you take the spectrum of the counter, and you see lots of neutrons. This is this big bump. When you go underground, and we did study that at different underground locations, Curve in Virginia, LNGS, Sudan mine, SURF, and the waste isolation pilot plant in New Mexico, which is actually the cleanest environment, despite the fact that it's the long-term storage for the US military nuclear program. You can imagine what's down there, but that is the cleanest environment. I was really impressed about that. You see all these neutrons are gone. So what are we using for neutron detection techniques? First, we are pretty conventional. We use 24 helium-3 tubes embedded in a polyethylene matrix. Here's basically, that's a matrix, that's the internal matrix. We drill a hole, and that where the tubes are, helium-3 gas tubes, 24, and There is a paper about that. It works very efficient, but it only counts the neutrons. It doesn't give you information because these things are for thermalization. So you thermalize all the neutrons, you don't take a spectrum, so you don't know where they're from. Okay, they can also be from background reactions. So that's advantage. It has a high efficiency because of the 1/v law, but it is has no, you have no capability for identification of the neutron source. So therefore we switched to deuterated polyethylene detectors, which were developed together with Oak Ridge. Mike Febraro is the head guy there. And you see these, the different test experiments. This was at the beginning, we were rather preliminary, and now a more sophisticated device of many of these polyethylene. They are special liquid scintillators, those, and literally home built for doing these experiments. So that are the backbone of the experiment that allows you to do angular distribution, so it really allows you to identify the different reactions. And then in addition, in Frankfurt, I was on a sabbatical, we implemented helium-3 spectrometers. They are kind of like the helium-3 tubes, but they are only larger in diameter, and you do spectrometer of the protons because you run on the helium-3 PN reaction, or sorry, NP reaction. So you do the spectrometry of the protons in a proportional counter to distinguish between the different sources. So with these detectors, the polyethylene detectors, we can unfold the neutron spectrum. We develop the codes. And from the unfolding of the neutron spectrum, you can distinguish between the boron 11 alpha N, the boron 10 alpha N that was on the boron target, and the carbon 13 alpha N from impurities. Okay, that's one of the strongest reactions always is impurity, so it was important to separate that. So it took us some time to really find the right codes, develop the right codes for doing that, but it works rather well. These detectors, they do it naturally. You look at the spectroscopy with the natural boron target. You see here the thermal neutrons, but you see also the boron 11 alpha N, and here the boron 10 alpha N. I mean, these detectors are difficult to get. They were developed actually in Israel 30 years ago, and you see it's pretty banged up. I inherited that detector from Mainz, and they went out of production. The Israeli company, I don't know what happened, they just disappeared from the market, but now you can get them in the US. They have kind of a license. Anyway, so let me focus on the boron 10 alpha N reaction. Here's basically the compound nucleus, and should have marked the Q value. Here, here's the Q value. Yeah, for the boron 10 alpha and 0, and then you can have alpha N going to nitrogen 13, alpha D going to actually should be carbon 12, not nitrogen 12. And to alpha P going to carbon 13. And so we did these experiments. That was the previous data, the gray point, 1973. So we pushed further down, and you see an enormous increase in cross-section down here. And that increase is presently interpreted as a really broad cluster resonance above the Q value, above the alpha threshold in nitrogen 40. Okay, so we did a selected R matrix fit. We observed this increase also in the alpha P and in the alpha D channel, and we pushed it down. We tried to go down as far as possible with our accelerator. That's literally the limit. That's the S factor. That's a conversion of the cross section into the S factor by taking out the effects of the Coulomb barrier. You actually have exponentially decreasing cross section. You're really at the limit of the counting capability, but by taking out the Coulomb barrier, you get a fairly flat curve, which is better to display. So you see that all in the alpha N, alpha P, and alpha D channel. So we believe that's a strong possibility for facilitating a transfer from lithium to the CNO range. However, there's a problem you also have when you produce boron 10. That's the uncertainty right now as we determine the alpha N reaction. And that is, this broadband is in the uncertainty of how to interpret this. That's our best fit, but you're still pushing for lower energy data. One of the problems is if you have protons in your environment, and typically you would assume you have protons in the primordial material, lots of protons, it also is dominated by alpha cluster structure. Here this bamba, lots of alpha cluster state, which decay by the boron 10 p alpha reaction to beryllium 7. And here the threshold, that's a 10 keV resonance near the threshold, that's why it goes up. And you calculate the reaction rate. You see here in blue, that's the boron 10 p alpha, and in black and red, that's the boron 10 alpha p or alpha d. And you see in temperatures of early stars, that's about here, you have about 5 orders of magnitude difference. That has to be reduced, otherwise the boron 10 is eaten away immediately by proton capture. So that's where the convection comes in. And that's what we're simulating right now, that these convective processes generate bubbles, helium-rich or hydrogen-rich bubbles where these reaction chains can be operating. So we did measurements, the carbon-13 alpha N. It's the same case in carbon-13 alpha N as you see here. Carbon-13 alpha N is here, the pink line, that's a reaction cross-section, and the carbon-13 p gamma is here. Orders of magnitude larger, about the same number of order of magnitude. And here also you need a separation of alphas and hydrogen to facilitate the alpha N reaction source. In S-process stars, during helium burning, by mixing hydrogen into helium-rich environments, so it's a kind of mixing process. You produce carbon-12 p gamma, so you make carbon nitrogen 13, which decays to carbon 13, and then you make carbon-13 alpha, and that's the present theory. Here you see basically the up to last year extrapolation of the reaction rate. So you have all these high energy data. Again, the S factor. Here you see literally the cross section that's converted into the S factor, and that gives you that. And then low energy data with huge error bars. That is where we anticipate the reaction to become important. And that's why people go underground, and to see if that's a real extrapolation, you see that's the uncertainty bar. You cannot even exclude threshold. So this increase is coming from a sub-threshold resonance. That's the speculation here. So that is, on the right-hand side, you see a lot of experiments we have done at Notre Dame facilities to map the impact of the higher energy cross-section. And you see that's from alpha energies at higher energies. And the main interest was there that several of the neutrino experiments corrected for neutron impurities in the neutrino spectrum. And that is mainly from the carbon-13 alpha N reaction being produced by natural alpha decay in rock material. And they took the red line, which is based on Haraldsopoulos analysis some 10 years ago, which measures the total cross-section. And we showed that that is not quite true because that is mainly the cross-section to higher excited state, which don't generate high enough neutrons to impact the neutrino spectrum. So that has to be corrected in the neutrino observations. But our main interest is the extrapolation, the impact to lower energies, and we just published a paper where we do this prediction here that the cross-section, the low energy cross-section is actually below these data, at the lower end of these data. And that is literally limited by a paper by Avilite measuring the ANC asymptotic normalization coefficients of the subthreshold resonance. This is confirmed now, literally, but I don't want to talk about that, but because it's still not published, I have been hoping that it would have been published by now. So it's confirmed by two independent experiments, underground experiments, but it's still in analysis. So let me come now to the consequences. I will split that in two parts: carbon-oxygen production in the early universe in first stars, and the subsequent nucleosynthesis. So that's the alternative path to the triple alpha process, which I highlighted earlier. And that is the lithium-6 capturing an alpha particle, going to boron-10, and another alpha particle going to carbon-12 under emission of a deuteron, or going to nitrogen-13 with emission of a neutron. Different reaction channels, they are about equally balanced, 30% deuteron production, 30% hydrogen, 30% neutron production. So you have these three reaction channels. So we measured those, as you have seen, and then we couple that with a nucleosynthesis simulation for an early star environment, where we reduce the proton hydrogen component being in one of these bubbles. And you see, basically, you can bridge, depending on the strength, you can bridge the mass 5 and mass 8 gap. And you go, after 1 hour, you are burning, you are you're basically in the boron range. And after 10 months, you have a full-flown nucleosynthesis path bridging the mass 5 and mass 8 gap. 10 months is a relatively short period, so it's a time scale of the dynamic convection. So it's entirely, from these simulations, entirely feasible that you have local bubbles of material where this burning is being facilitated. These calculations are extremely complex because you have to do it in 3D dynamics and coupling a nuclear reaction network to it. That is a challenge for even the biggest machines. This is what the abundances say for these kind of simulations. You start with the primordial abundances, helium-3, lithium, and don't plot all of that. So hydrogen and helium is up here somewhere. And you basically, you see, you convert it into beryllium-7, you convert it into lithium-7, and lithium-6 here is immediately further converted to boron-10, and then eventually here to the nitrogen-14 range. Boron-10, boron-11, you see both. I should have highlighted the boron-10. And eventually to the nitrogen-14. And then you are in the CNO cycle, and you establish a CNO that is about logarithmic scale, 10 to the 4 years. You establish a CNO material and an equilibrium between the material, and then you can go from there. There are two paths on. You either can produce carbon-13 and make an alpha-N reaction because you are in a dynamic alpha helium-rich environment, forming neutrons, which can facilitate the eye process, or you can make that nitrogen 14 alpha gamma forming neon 22 alpha N, eventually also producing neutrons. Or that's an alternative scenario. If these branches don't operate, you can make the fluorine-19 P gamma reaction, which would be a breakout from the CNO cycle on the charged particle side. And we didn't think that was possible for the longest term because neon 20 is an alpha cluster nucleus, and we anticipate that there would be a strong P alpha reaction, but recent underground measurements showed that there is actually strong P gamma resonance, which could facilitate that. But we're still in the analysis of that scenario. I just wanted to mention it. So it's very complex. And here's what you get in the observations. That there's this two-star observation. You see here CNO material. And that depends really on what moment, what age you observe these stars. And here this one has less CNO material except in the carbon-12, that's comparable. And you see here the higher abundances, which could be due either to the breakout from fluorine-19 or due to the eye process. Before we get to that, let's talk about carbon-12 alpha gamma. It's a holy grail for the entire astrophysics, as Willy Fowler supposedly once formulated. I never found that quote, but people quote him. Anyway, it's important for late stellar evolution. It determines the carbon or oxygen burning phase in late stars. It's important for the ignition, and this is important for the ignition of type 1a supernova, because that depends very much on the carbon-12 abundance and the oxygen abundance ratio, which you see here for 30 solar mass star calculation. So here's the uncertainty. You see, due to the carbon-12 alpha gamma reaction, lots of O16 is produced, and there's much more O16. You could envision carbon burning being facilitated through the carbon-12 plus O16 fusion rather than through the carbon-12 fusion. So that's in the uncertainty range. So that's what people are grappling with. And also the ignition condition for type 1o supernova. Type 2 supernova, it's basically the shock front nucleosynthesis of the emerging shock front through the outer layers of the pre-supernova stars, which affects the abundances here. And one more recently interesting, it's not a recent idea, it was formulated by Fowler and Euler already in '64, but now they have a new observational tool of the massive black hole gap, which is literally determined, sets the limits for pair production supernova, which literally rip the entire star apart and don't even leave a black hole. And that is facilitated, this limit is facilitated by carbon-12 alpha gamma. There's a recent paper by Farmer et al. So the carbon-12 alpha gamma is determined by its cluster structure of O16. Alpha plus carbon-12 forms O16. And here you have the compound nucleus, that's the alpha threshold. And you have several interfering resonances and subthreshold states. That are the typical cluster structures, a ground state, and one high excited state where sort of have a chain of linear chain of alpha particles. These guys are more complex. You see here a simulation of the alpha cluster structure. And what you see, what determines the reaction rate is interference in two waves. The so-called E1 term is interference between 1 minus resonance and 1 minus subthreshold states. The question was always, is it a positive or negative interference, which dominates the reaction rate here. And here 2 plus state resonance and a 2 plus subthreshold state, plus the direct capture, an E2 direct capture, which is also interfering, and there are similar possibilities. So the problem, like in all of nuclear astrophysics, the problem is in extrapolating it to low energies, because we cannot really measure just to low the cross sections. I mean, they're associated with the lifetime of stars. So they're just too low to measure them in the lab. So we rely on theoretical extrapolation with all its uncertainties. And for that, we developed basically the Azure multi-channel, multi-level R matrix program to look at the compound nucleus and all the different reaction channels feeding it, covering the entire gamma window. That's a range where the reaction is supposed to take place in stars, over all reaction channels and fit that parallel, all the existing data going back to the 50s. And you see here the direct measurements, E1 and E2, that are the existing data. We want to know it here. And here you see elastic scattering, alpha gamma reaction, N15P gamma reaction, alpha reaction, elastic scattering, inelastic scattering, all sorts of things we fit parallel, including also the beta delayed alpha decay to these levels in beta decay to these levels, so 60 with the subsequent alpha decay. And that is basically the conclusion. We have an E1 term that was published in 2017 in a review of modern physics. That's a black is a E1 term, and red is the E2 term, and blue is an additional contribution from cascade transitions to higher excited state in the 6 MeV range. And this is basically the cross section. That's the S factor extrapolated. That's where you need them. But it's still a large uncertainty associated with the input uncertainty. So we talk about now 15, that is conservative, 15 to 20%. This is the uncertainty range of this analysis, all relative to a Notre paper by Angulo et al. 1999. That's a previous uncertainty range by Kunz et al. That was a German collaboration. And this is a paper up here. And when you take these data without the uncertainty range, you see basically that the ratio of O16 of carbon-12, which you will develop in these kind of stars based on the reaction rate. Let's talk then about the I process in early stars. So the I process is facilitated by the fast convective environment in early stars. And the idea was literally that you have basically, it's more convective than this, that was just a draft, that you have here sort of a hydrogen-rich zone, here helium-rich zone. You mix hydrogen in the helium-rich zone. The helium-rich zone is carbon-enriched. So you make carbon 12 plus proton forming nitrogen-13, and then that nitrogen-13 is mixed down into hot environment. So it requires a fast convection scale. That's about 9 minutes here. And then it decays in the hot environment to carbon-13, and then it makes alpha capture, forming alpha N. So it's similar to the S process, only that you have a fast mixing environment, which gives you the time scale to bring nitrogen-13 down into hotter regions before its decay. So that's the difference. But that makes a world of difference in the production of neutron. You get a much higher neutron flux, 10 to the 15. There are several orders of magnitude higher than in the S process. And that sort of seems to match, produce an abundance distribution, which matches the abundance distribution in early metal poor, which means old stars. And then the other process you can have, you can not only mix protons and hydrogens, you can also mix other primordial abundances, lithium-6 and boron-10, into these zones, and then facilitate under helium-rich position the reaction sequences I lined out before. So it may go parallel, it may be just a speculation. It requires better simulations, and we are working on that. This is one of the simulations, And you see here basically helium-rich zones and hydrogen-rich zones. So the hydrogen-rich zones are basically the blue ones. The helium-rich zones are the red one, pink ones. So that will be coupled to a reaction network. It has been coupled already to, in terms of the carbon-13 alpha N reactions for the I process. And here you see the I process reaction path, because you have a high neutron flux. It's running along the neutron-rich side of the line of stability. And that is a prediction compared with the observation of one of these early metal-poor stars, and it seems to be in good agreement. Okay, so as I said, that's a preliminary version. Right now, we are working on looking at other neutron production reactions. So this is a process in project in progress. So here you see basically another simulation. They produce lots of colorful pictures, but the challenge is not so much the colorful pictures. They have that now down. Now the challenge is to couple that with a nucleosynthesis network, with a full nucleosynthesis network. That one is an easy one. It's limited. Now we want to go to the next step, make a more complex reaction network. And here you see the first event. You see basically calculation showing the bridging through different reaction channels of the mass 5 and 8 gap, facilitating the conversion of primordial elements to CNO elements. Okay, here you basically see the onset of CNO cycling. So that is in process. It's a very time-consuming activity. Okay, that's my conclusion. The first star environment, it provides absolutely new and different nucleosynthesis conditions, basically because you have a different fuel than in normal stars, and you have different dynamics due to the convection and contraction under which you operate. Mass 5 and 8 gaps can be easily bridged on different time scales. The triple alpha process, because the 3-particle interaction is slow, so you can do it much faster by alpha capture on lithium and boron isotopes, but you have to remove, has to happen in a hydrogen depleted zone. So the neutron production is possible for the I process by these new reactions, boron 10 alpha N reaction, and also boron 11 alpha N reaction, which I didn't mention here. And so, but you have to do that in a 3-dimensional dynamic simulation environment. That is a present challenge. So for the experimental effort, we need to push the data to lower energies. You could see we only map the high energy tail of the resonance. It's entirely possible that that resonance is at lower energies, and then it could enhance the reaction rate by orders of magnitude. That needs to be studied in the next experimental round. Okay, with that, I want to thank you, and I want to thank all my collaborators for the experimental effort, the Notre Dame team, also with collaboration of Oak Ridge and Axel Bölzig, also former postdoc. He's now at the INFN Gran Sasso, and also for many discussions with other teams, underground labs, and theorists across the globe. Okay, thank you. Thank you for your attention.
Okay, thank you, Professor Wiescher, for a very nice and comprehensive talk. I suggest that participants who want to ask questions could either put it in the chat, or if you're there on Zoom, you could also ask the question yourself. So in the meanwhile, I will also look for questions on YouTube, but maybe we start off with any questions on Zoom for people attending through the Zoom platform. So is there anybody who wants to ask a question? Okay, while people are thinking about
Yeah,
questions, let
I,
me
I have
ask.
one question.
Yeah, sure. Please go ahead.
See, for the low
Mr. Pali.
energy, yeah, yeah. So for the
Yeah.
very low energy cross section estimate, what is the chance for the indirect methods like Coulomb breakup methods to give a right reliability of the indirect methods to give cross section at very low energy?
Sorry, can you repeat that question? Acoustically, I couldn't quite answer.
Yeah. The question is for the low energy estimate for the cross sections, what is the reliability of the indirect methods to give the correct answer for the cross sections?
I mean, personally, I mean, it's a question of reaction theory. And also in my mind, it's also a question of how good do we know the physics of reactions near the threshold? What comes into it? And there's even simple questions such as how well do we know the Coulomb barrier for extended nuclei at low energies? For example, this question becomes very important when we look at fusion cross-section between extended nuclei like carbon-12, but also carbon-12 plus alpha could be affected by that. So, and then the question of interaction with the electron shell, which provide a screening effect for the interacting nuclei. How well do we know that? There are some very simple models there, but they usually don't match the data. And in our R matrix approach, how well do we know the potentials there? So there are all sorts of questions, and I really cannot reliably answer your question. I mean, we just don't know, I believe. I mean, we go with the present knowledge, and as we all know, the nuclear reaction theory was developed in the 1930s, and we're still using kind of the same, maybe a little bit more sophisticated codes, but many of the old assumptions are in there, and they have to be gradually removed as we go by step. Nuclear reaction theory is not a high fashion topic these days, unfortunately, and but I think it should be, in particular in nuclear astrophysics, because there's a lot to study and a lot to investigate. So we learned a lot about the nuclear structure by indirect techniques like the ANC measurements or the Trojan horse approach, which tells you experimentally about the cluster structure, but then you have to translate that into nuclear reactions, and then you go back to the same old energy sources. It was demonstrated quite visibly in a recent paper exchange with respect to carbon-12.
Thanks.
Okay. There is a question by Mahuli Datta. Are you there? I mean, would you like to ask the question yourself, or shall I read out the question?
It's Shaumen Notre. I wanted to ask, so you had an early slide where you showed a reaction process and the R matrix calculation prediction for it. It was titled The Predictive Power of R matrix Calculation. It looked pretty amazing. So I just wanted to know what were the inputs? I mean, how much of it was first principle calculation and how much was like,
it was actually first principle calculation, and it was published last year in PRC, the carbon-13 alpha. I should have given the references here.
So what were the inputs?
In PRC, Debo et al. So it's the first principle calculation, and the experiments, they were done later. And what I showed was literally just an overlay between the new data and the experiment, but I didn't want to really show the new data because I was hoping they would have been published by now, but they're not, so that's why I kind of blended them out. So I don't want to take that away from the authors. So that should be published soon in PIL, I guess, if the referees agree, as usual. So it was actually indeed an amazing confirmation of the R matrix technique.
Can we take some YouTube questions, Professor Wiescher?
Yeah, fine.
Okay, so there are two questions there. One is by Abhinav Chaudhary. He says, in addition to the contribution of the total energy density, do electron neutrinos and antineutrinos also play a special role in the production of helium-4 during the Big Bang nucleosynthesis?
Oh, the Big Bang nucleosynthesis so far is primarily neutron-induced reactions and the proton-induced reactions and other light ions. So there are different interactions. So the network is, and the experimental investigations have been pretty complex. Neutrino and electron-induced interaction was in the earlier phase and before the decoupling of the weak interaction force. So I think that was literally in the first second. And then you have basically, you freeze out neutrons and protons as a ratio which is determined by the mass difference. And so neutrons are less abundant. And then in the third minute, you basically freeze out the photon-induced coupling, which causes the disintegration of deuterons, and that is the first step. That's the third minute. That's when the charged particle-induced nucleosynthesis starts in the third minute, and the decoupling is, I believe, in the 10th minute, something around that. And then you literally have to wait for the formation of first stars to reach again the high-density temperature environments where you have nuclear reactions taking place.
Okay, thank you. There's another question by Abhijit Wiescher, which says that by extrapolating R matrix predictions, we see that there are resonance structures very close to the alpha thresholds. What is the physics behind that?
R matrix is a phenomenological theory. So it is only as good as the input parameters, as I would say. So we try to, it was developed by Eugene Wigner, and the first big paper was in the 50s by Lane and Thomas. And it's primarily developed for fitting the cross sections. So, and we expanded it by fitting all channels parallel, and that includes channels which are not directly associated to the reaction, but directly associated to the compound structure of the nucleus. But the input parameters are extremely important, and that includes right now not only the reactions, fitting the different reactions, but it takes also into account nuclear structure parameters observed in indirectly probing the compound nucleus. Like in the case of carbon-13, we took the ANC strength of the subthreshold resonance, and in other cases, we take all the indirect values into account, and that allows us to look directly at the threshold. But we only interpret it within the limited theoretical capabilities of the R matrix. So there may be, keep warning about that, there may be inherent theoretical uncertainties in there, which we don't know. So I keep pushing that we have to look for that. Yeah.
Okay. Are there any other questions on Zoom? In the meanwhile, let me ask a question myself. What do you, in your view, are the major, problems, outstanding problems in nuclear astrophysics as of now? I mean, of course, it's
I think
probably difficult to give a quick answer, but at least some of the.
I think a
major
fundamental problem inherent to it is that we need to understand the low energy, the quantum impact on the lower energy extrapolation. That's general. Then the critical one is still carbon-12 alpha gamma. The problem is we are driven by the observations, and the observers have better and better instruments, and that the modelers get better and better codes, bigger and bigger computers, and they want lower and lower uncertainties. So they ask for uncertainties in the 5% range. Based on all of our inherent uncertainties, we are in the 15% range, so 10% to go. So that needs to be improved. In terms of reactions, I'm very much interested in neutron production reactions, because that defines the neutron reaction flux. And you have different neutron reaction flux, the S process, the weak S process, the I process, the N process, the R process. They all have their own specific neutron sources, and that needs to be understood better than we know now. And then I believe in the strength of low energy charged particle reactions during the different burning phases of a star, because they set literally the fuel conditions for the subsequent burning, and also the fuel conditions for explosive burning. And I know it's big fashion now, charged particle reactions far away from stability. But when you have an explosive process, I mean, you have lots of possibilities for the reaction path. So the key reactions in my mind are the reactions where you funnel or channel the reaction path. So other reactions which determine the flow. You can imagine that as a flow diagram. When you have a broad flow, the reaction flow takes the path of the least hindrance. So a single reaction doesn't make much of a difference. Like in an explosive environment such as the R process, single reactions are of secondary relevance. But in stellar burning, where you had low temperatures, there are many critical reactions occur. That's why I moved back literally from studies of explosive nucleosynthesis to study of stars again.
Okay, thank you. There is a question by Mallika Kaushik. Would you like to ask it yourself?
Yes, sir. Thank you. Thank you, sir, for giving such an informative talk. I would like to ask a question in regard with one of your slides. You have presented 9 boron plus alpha reaction plots, right?
Say that again. Which plot?
10 boron plus alpha versus 10 boron plus proton reactions.
Oh, the different alpha N reactions, yeah. Mm-hmm.
Yeah, so there you have given 2-3 plots where you have given angle for these 3 reactions. In these 3 reactions, you have alpha N giving nitrogen 13, and another panel. It is good if you go back to that slide.
Fine. Tell me when you see the slide.
Yeah, sure.
I think I know which one it is. This one?
No, sir.
This one or?
No. Previous one.
Did I miss it? I think there's not much before that.
No, I think we have missed it.
You said that there is an angular distribution there, is it?
There's
I
a
thought
10
that-
boron.
I think here shows the different angles.
So the heading of
There are
the
two
slide
angles.
is, yeah, you can also see this graph here. The 3 panels, right hand side, there is 10 boron, alpha, and giving 13 nitrogen, right? And in the second panel, this 13 carbon, and in the third panel is 12 carbon. And so this theta lab is 0 degree, and then 135 and 90. It means it is the same reaction and we are getting different products at different angles, is it?
I mean, the angles are only defined by the experimental arrangement, and we measured then independently a broad angular distribution, because the angular distribution is also being fitted in the R matrix, and that is just, 3 angles picked from that. But we have for each of the channels has its own angular distribution, which is part of the fit then.
Means in the same experimental setup, we are going to have all 3 different channels at different angles. Is it? Am I getting it right, or it's something else?
Here you see the setup that gives you the angular distribution. That is for the neutrons. For the particles, we had a sort of a standard kind of a OTEC chamber with internal particle detectors.
Okay.
I think you meant this one, huh?
Yes.
Yeah.
Okay, and so this S factor, what precisely means this S factor? Is it like it's a different presentation for cross section, or it's just having different?
So the S factor is just I should have made a slide for that. It just takes the cross section times and then it's corrected for the de Broglie wavelengths. Times e to the minus 2 pi eta, and 2 pi eta is first order approximation for the Coulomb barrier without taking into account the orbital momentum barrier. It's a textbook definition, and the only it was invented in the 50s just because they didn't have the computation power to extrapolate the Coulomb barrier. It just takes the Coulomb barrier out and allows you kind of a flat, semi-flat extrapolation. In the beginning, they just didn't know how to extrapolate. They did high energy measurement, and then they did a kind of linear extrapolation, and deviations from the linear extrapolation were explained as due to orbital momentum barrier and things like that. But we learned in the last years with the underground labs that the structure at the threshold is much more complex and has much bigger influence than ever previously thought.
Okay, thank you.
Are there any more questions from the Zoom audience? Because I went to the YouTube, there don't seem to be any questions there. Anybody in the Zoom audience would like to ask something? Okay. I have a question, but maybe I can ask that of Michael after the talk. So we have already maybe exceeded about 20 minutes. So let me thank Michael for this very nice talk. And we hope that we will get you again, on maybe either on this forum or some other forum on some of the other topics that you could talk on.
Yeah, we'll be happy to do that. Now I'm used to getting up early, so.
Thank you very much also, yes, for this getting up early. This is the perhaps the convenient time. Yeah.
Thank you. Thank you for the hospitality over distance. Yeah. Okay, bye.
Okay, so we close this talk. But I'd just like to ask you something about this radioactive ion beam facility. What more would it bring to the table? Because obviously you will not be able to measure cross sections near the gamma peak, certainly not with the intensities of the radioactive. So you would have to perhaps do indirect measurements, right?
Oh,
Or maybe
indirect
other
measurement.
measurements, which are
Yeah, indirect measurements are much more powerful, actually much more powerful than I initially thought. You know,
Mhm.
I'm a representative of the direct measurement community, so
Mhm.
I think it has to be a concerted action, combination between direct and indirect measurements. And so the indirect measurements, their shortcoming is they measure the structure near the threshold, but then they have to match to the direct measurements.
Mhm.
And then it is very much theory dependent how you convert their data into reaction data. How well do you know the reaction theory behind it? And actually that was demonstrated rather vividly in a recent Nature paper where the Catania group made an indirect measurement of the carbon-12 fusion reactions.
Mhm.
But that triggered a large rebuttal from other communities which claimed their interpretation, their conversion from the structure data to reaction data is not correct. So that underlines my claim that there are much more theoretical uncertainties. That needs to be understood. So problem is in the detail. And several questions point out to that. The problem is really how much trust you the extrapolation procedures which we are using presently. That includes my own extrapolation procedures.
Are there any efforts to maybe have different approaches to reaction theory in terms of, let's say, using semi-classical methods in the complex plane and so on?
You mean in
The methods which were pioneered, I think, by Berry and company a long time ago, but
yeah,
which
there are
were not that popular at that time, I think.
yeah, there are a
Or
number
while.
of different approaches. You see them. Yeah, there are a number of different approaches. I can't quote them offhand now, taking more things into account, but it's just the beginning right now. So, I mean, I personally am very much interested in cluster structure. How well is that translated? And then, of course, when you have clusters, I mean, fusion in clusters, in the carbon-12 case, I mean, we're doing right now a bunch of experiments to that.
Mm-hmm.
I mean, you form that is facilitated through carbon-12 clusters in magnesium-24. And then how is that coupled to the decay into the alpha channel? Carbon-12 is, again, alpha cluster. So how is that transition? And then, of course, you have something, effects like the so-called hindrance effect when you smash two expanded nuclei together. There, in heavy ion fusion physics, they observe something like a hindrance effect that the cross-section is decreased, and that is associated with the incompressibility of nuclear matter. So it kind of bounces back. We know that that happens in neutron stars and supernovas. So they claim it happens also in fusion reactions. So what is the impact of that in low temperature fusion? There's a pronounced hindrance effect that would translate into 3 orders of magnitude reduced reaction rate. So there are all these open questions which are presently debated and which frankly need a better theoretical interpretation. So I'm not the theorist, I'm doing the experiment, but I think that's what is needed. We need better theories.
Okay, so thank you very much, and
Thank you.
yeah, thank you. We we will close on this note.